Hello ladies and gents, and welcome to video number 103. This video is on velocity time graphs, and it's about the area underneath the graph. Keywords here are velocity and area under the graph. So velocity is like speed, but it is a vector quantity unlike speed, and a vector quantity means it's got direction and magnitude. Alright, just like in the film, the baddie called Vector. Now, the area under the graph represents the distance travelled. Okay, so the distance travelled can be found if you work out the area between the x-axis and the graph itself. Okay, velocity time graphs plot velocity, sometimes labelled as speed, against time. So velocity is on the y-axis and at time is on the x-axis. You might be asked to work out three different things. We did the last two things in the previous video. So if you're not sure what they are, go back and watch that one about rates of change. So this is the last of the three things. Now, what we're going to do is we're going to split the area under the graph into different shapes that you know how to calculate the area of. So rectangles and triangles would be lovely, but trapeziums are also very useful. And then we're going to add the area of the shapes together to get the distance. All right. Now, if you've gone above the graph with the shapes that you're drawing, you're going to have an overestimate for the distance. And if you've gone below the graph with the shapes you're drawing, you've got an underestimate for the distance. All right. And that should all make sense when you see it in action. So let's have a look at the first question. I will zoom in to that one. Okay, and then what we'll do is do the calculations for the areas of the shapes and then add them together and we'll get the distance. So this is a particle. This graph here is the velocity of a particle going quickly, then slowing down, then going quickly, then slowing down again a little bit, then going quickly, constant speed here, and then it's slowly starting to stop, and then starts to decelerate, and then it just stops completely. I'm not sure what's happened to the particle at that point, but that's the last number that we've got on there. So what we need to do is find the distance that's travelled between 2 and 5 seconds. So let's get the shape tool out so I can draw some shapes. The line tool, I'm going to draw a line that goes up to here. All right, so between 0 and 3, so that length there is 3. All right, I'm going to then join that up to there. I think, yeah, we'll go to there, all right, to 6, and then I'll go down here, all right. So I've gone a little bit over the top of that line there, and I've got a trapezium, all right. What I'm then going to do is I'm going to draw another trapezium from that point there, and I'm going to go to there, and then down to 4. So we've got equal widths on our trapeziums, and then I'm going to go to there. All right, so what we've got is this kind of 3 trapeziums that we need to work out the areas of each of those and add them together to get the distance that's been travelled, or an estimate for the distance that's been travelled. So this is something you should know how to do already. If you're doing some grade 9 maths here in this particular section, you should know how to work out the area of trapezium, but there will be a video on it, so you can go and watch that. But I'll just run through it quickly. You add the parallel sides lengths together. So this side and this side for the first trapezium are the parallel side lengths. We've got 3 plus 6, and 3 plus 6 is 9. All right, you half that answer to get 4.5. You multiply it by the height, which is 1, which is useful. So what we've got there is just 4.5. So I will write down 4.5, and the units will be in meters, because the velocity of the particle is in meters per second. All right. Now we need to get the second one, and that is going to go from 0 here to 6, and then from 0 to 9. So we add 6 and 9 together. All right. We get 15, and then 15 divided by 2 is 7.5 meters. And then we'll get the third one. We'll do exactly the same thing. So we've got 9 plus 10 is 19. And 19 divided by 2 is 9.5 meters. And we've got the areas of all 3 trapeziums. Add them together and we've got the total distance that's been travelled by the particle in that particular time period between 2 and 5 seconds. So add the halves together, 1.5, 11, 20, 21.5. I think 21.5 meters would be the answer that we would give there. All right, and is it an over or an underestimate? Well, it's tricky to see. We've gone over here, we've gone quite a lot under here, and then we're pretty much bang on there. All right, so what I would say is we're just an underestimate. All right, and I'm just going to underline the word underestimate, so you can not watch me have to write the word underestimate with this dodgy mouse. All right, done a pretty decent job there of keeping it as neat as I can. Anyway, that's the first question. Hope all that makes sense, as I always say. Let's have a look at the second one. All right, so in the second one, we've got to estimate the area under the graph between 0 and 2 seconds. So this one doesn't say anything about the distance. It just says estimate the area underneath the graph between 0 and 2 seconds. Okay, so what we'll do is we will take the tool again, and we'll go between here and here, 0 and 2, and then we'll draw a line up there. Now I would probably just draw a triangle there. I think that's probably good enough. You could draw a triangle there, and then a trapezium there. Maybe we could do that. So we could have a triangle here to here, because we did cut off quite a lot of the graph there. So there's a triangle there to there, and then a trapezium there to there. That's probably a better estimate. We'll use that. Okay, and it's gone slightly underneath the graph in both instances as well. But we're just estimating the area underneath the graph, and let's use that as our shapes that we've drawn. Okay, so this triangle here is 1 multiplied by 6 and then divided by 2, so that's 3 units squared. I'm just going to put units to the power of 2 because we don't know what the units are necessarily. And then this one is up here at 6, and this one is up here at 9, and 6 plus 9 is 15, and then 15 divided by 2 is 7.5, and then we multiply by the 1 as well. So that's units squared as well. So what I would say is it is 10.5 units squared. Okay, now state what your answer to A represents. What we should know now is, because what I've taught you, is it represents the distance travelled. I'm just going to write the word distance, but you should really write travelled as well. There we go, nicely joined up writing with my lovely mouse. And that's the second question. Let's have a look at the third question. Now the third question is really quite tricky. All right, I'm not going to zoom into this one. I'm going to write on the pad for this. Just get rid of my son's car that's on it. There we go. Right, let's see if I can get out of this mode. There we go. And I'll move myself over so you can see the third question. Right, so this third question, the graph shows how long it takes my wife to run 200 meters. All right. She's pretty quick, my wife. Got to calculate my wife's maximum speed. All right, so that's this point here on the graph. You can see that's the maximum speed, and then she just maintains that maximum speed until the end of the race. So she gets, this is what the graph's telling us. She starts off, she's accelerating the whole time until this point here, until 5 seconds in, and then bang, she's just running at that same maximum speed until the very end of the race. And that's not exactly how it goes, right? And that's probably why we've got this labeled as speed rather than velocity, all right? But yeah, let's try this question. Difficult because we've got no scale up the x-axis here, all right? Sorry, y-axis. I'm distracted by the pen being rubbish again. Right, give me a second. Let's try and fix this. Right, here we go. So no scale on the y-axis. So we need to know what that is. I'm going to label that as x, okay? And we do know what the distance is underneath the graph because we know the whole race is 200 meters, all right? So this triangle here and this rectangle here would add together to make 200 meters, all right? We haven't got what that measurement there is, so we're going to have to write some expressions, collect the expressions together to then form an equation and solve the equation to find out what x is. That's what this one's all about, all right? So I'm just going to pause because I can see we've got some awkward numbers here with the time. I'm just going to pause this video, going to get my calculator up, and I'll be back in a second with that, or back in a millisecond for you. Boom, as if by magic, there it is. So the yeah, the equation that we need to write is going to start off with knowing how to work out the area of a triangle, and then form an expression for that. So what we would normally do is we'd multiply this by this and then half it. Okay, so 5 multiplied by this, which is a difference there of x, isn't it? And then half that answer. So half of 5 is 2.5. I'm going to write that as 2.5x. All right, that's the expression for the area of this triangle. All right, what I need to work out is the difference here, right, between 24.25 and 5, which is 19.25. And I need to then multiply it by x to get the area. All right, so that's going to be plus 19.25x, and we know that's going to equal 200 meters. All right, so there's my expression, or my unsimplified expression, for the area underneath the graph. And here's the actual distance for the area underneath the graph. All right, so if I add 2.5 to 19.25, I get 21.75. So 21.75x is equal to 200 meters. Fly in my face. And then we divide by 21.75, so the 200 divided by the answer is what x is. All right, so x is equal to 9.195. I'm going to round that to 9.2. 9.2. I'm just going to say what I rounded it to. Yeah, that is correct. 9.2 to 1 dp. Okay, so to one decimal place, that is our value of x. Okay, and that is the maximum speed in meters per second that she's running, because that is the value of x, and that, like I said at the beginning, all right, she hit that maximum speed there and maintained it until the end of the race. So 9.2 meters per second. Just to put that into context, the fastest man in the world, Usain Bolt, can run at about 10.5 meters per second. Okay, so 1.5 meters per second more is what Usain Bolt can do than my wife, which is crazy because my wife's very quick. She can beat me in a race. Anyway, question B, calculate the distance covered in the first 5 seconds. This should be pretty simple because we've got the x here. We know what that actually is now. All right, we know that's 9.2. So all we have to do is take the 5, multiply by the 9.2, and then half our answer. So I'm just going to multiply that answer there by 5 and then divide it by 2, or could have multiplied it by 2.5, and there we go. There's our answer to that. We know that the distance covered is 22.988. So I'm going to round it to 22 point. I'm going to say it's approximately equal to 23 because it's very, very close to 23 meters. So approximately equal to 23 meters. Okay, and that is rounded to the nearest whole number. There you go, and I hope all of that makes sense. We've done a lovely last question there, and yeah, we've got a couple of really complicated things that are going on, but it's just about working out the area underneath the graph. That's how you work out the distance that's been travelled, and that's it for velocity time graphs. One video to go. I hope you've enjoyed this one. We'll make the next one very shortly, upload them, and then in time there'll be linked resources for you in the description section. Continue to practice, be lovely to one another, and have a lovely day. Thank you very much for watching.